Okay. All right. Today we're talking more about our heat exchangers. Last time we kind of went through some examples and talked through here's counterflow versus parallel flow versus crossflow heat exchangers and some of the behavior associated with those. We did not get as far as actually solving for temperature as a function of position in a heat exchanger. So what we're going to do, at least to start today, is go through the method that you would use, like a control volume method, to solve for temperature as a function of position in a heat exchanger. And then hopefully we'll have a little bit of time to talk about what the solutions actually look like when you plot them out under different, say, effectivenesses or NTUs, and we'll talk about what that means too. Okay, so here's our energy balance on our heat exchanger. This is something we talked about last time. We have, usually we know coming into our heat exchanger, we know that there's some fluid at TH coming in. We know that there's some fluid at TC coming in. And then we probably know something about the mass flows of those. What we don't know is how much heat is actually transferred across the boundary of the wall. But we can do energy balance on each side of the flow, and we end up with an energy balance on the overall flow here for the hot side is Q dot, right? Q dot, this Q dot here is the same Q dot that's absorbed down here, right? That's the amount of energy that's transferred from one to the other. And those have to equal each other. And so we end up with, these two equations. And then we can go through and actually develop a third equation that we can use to solve for the heat transfer in a given device with its specific geometry. Remember, if we talked about one way to start that process is to think about the total resistance between the two flows. So you have, on the cold side, you have convection, then you have to go through the wall. There could be fouling resistances on either side of the wall. And then you have convection on the hot side. And that total resistance from one side of the flow to the other is related to something called the conductance, our UA. Our conductance is basically the product of the area times some effective heat transfer coefficient between the two streams. And so U times A. All right, so let's go through now and actually derive a solution for the temperature as a function of position in this. And so we end up with a third equation that we can use to actually solve this set of equations for our heat exchanger. So what we're going to do is we'll start off, here's our heat exchanger. We've got cold flow on top, hot flow on the bottom. What we want to do is same control volume analysis we usually do, but a little different now because we actually have two different flows that we have to worry about. So when we draw our control volume, we're going to pick a differential control volume in X. When we draw our control volume, and it's going to look, say, something like this on the cold side. That control volume, which is with, this is with dx, that control volume is going to be losing heat, or gaining heat, right? It's the cold side. It's going to be gaining heat from the hot side. So we want to think about a control volume that kind of exactly matches the amount of heat, exactly matches the position on the hot side. We have actually two control volumes that we're drawing, and we're going to say that there's some heat that's going from one side to the other, some little d Q dot, right? Some differential Q dot that's going from hot to cold. All right, we have now going, let me just actually expand this out so we can see it a little bit better. So let's draw like this. Okay, so we have our dq dot, that's going from hot to cold. We have to think about everything else that's going in and out of this control volume though. We have flow going across the boundary. So here, let's start with, start on the bottom with the hot side. So on the bottom, we have coming in some m dot h times enthalpy h, right? That's coming in at position x. Leaving here, we have m dot h I h. Let's just expand it out. So it's at x plus d m dot h I h dx times dx, right? That's what's leaving. So we have our Taylor series expansion of what's going out there. On the cold side, we have, let's see, we drew it up here. So the cold side, now we're thinking about specifically a counterflow heat exchanger for this example. If I go through this and switch the flows around, my governing and differential equation is going to be different. So if you have a parallel flow heat exchanger, the analysis is going to end up looking, the result is going to look a little different. The analysis is exactly the same. So here we have on our cold flow coming in, we have m dot c IC coming in here, and now this is at x plus dx, so we actually have to expand this out. And so this would be d m dot c IC dx dx. And so that's what's that's on the right hand side. So it's at the what are you saying? So it's at the x plus dx position. We have to write it in the expanded form because it's at the dx position. Okay, but we've drawn the arrow going to the left, and then on this side we have m dot c IC at position x. Okay, so this is our system that we've come up with here. We're not really including anything else. We're not including thermal generation in the fluid. We're not saying that viscous dissipation is important. This is kind of all we're saying is important for this problem. But we do have to account for this fact that the dq is moving from one to the other, and it's the same dq that's leaving or entering. So let's start then by expanding this out for the hot fluid. Okay, so first for the hot fluid, we write out the energy balance on the hot side, and that's going to be m dot h IH is equal to m dot h IH plus d m dot h IH dx times dx there, plus dq, or dq dot, right? That's our, it's going into, sorry, how did I draw this? Yep, no, that's leaving, so it's on the right-hand side with the other stuff. Okay, so that's our energy balance on the hot side. We can simplify this out a little bit, canceling out those terms, and we end up with just 0 is equal to m dot h d IH dx dx plus dq dot. Let's furthermore, again, make the assumption that this is an incompressible flow, and we'll use our specific heat instead of enthalpy. So then we get m dot h d c times t. So actually, this is bring the c out in front. So it's m dot h times c dth dx dx plus dq dot. And then let's use our, sorry, this is CH, right? C H is the specific heat of the hot fluid. So let's write this as our capacitance rate here. Let's call this C dot H. And that's the governing differential equation that we end up with for the hot fluid. We can do the same thing for the cold fluid. So for the cold fluid, it's exactly the same analysis, except that we have what? The signs are a little different. So I won't go through the whole thing because it's tedious, but here is what you end up with. It is on the left-hand side, now we have dq dot is equal to minus c dot c dtc dx dx. Right. So the difference now is we've drawn the arrows are in the reverse direction and the negative x direction for our flows, and then we also have heat flow entering the cold side as opposed to leaving it. So otherwise exactly the same analysis, but this is the equation that we come up with. Okay, so now we have here two equations. There are two governing equations, one for hot, one for cold. They both have to be solved, but they're actually coupled. Right? These are what we call coupled differential equations, meaning they're not independent of each other. The solution to one is closely related to the solution for the other. And in this case, they're closely related by this dq dot. Okay. So let's see, let's continue on and try to solve this now. Let's just rewrite our differential equations. We had dq dot is equal to minus c dot h dth dx dx, and we have dq dot is equal to minus c dot c dTc, dx, dx. So that's just what we did before. Okay, so let's introduce our rate equation here for Q dot. In our rate equation, what we want to do is think about maybe in terms of our resistance network. So we could write our rate equation, our dQ dot, as the following. We can write it as the temperature in the hot stream minus the temperature in the cold stream, and this is going to be at some position x along the path. So TH and TC are both a function of x. And if we write this in terms of a resistance, this is going to be what? So the total resistance for the full, let's see, look up here a little bit. So it would be the total resistance from, say, hot here to cold here, but scaled in proportion to the length of the control volume. So we could write this as our total times the length of the control volume divided by dx, right? So this is scaling the resistance. And think about, why did we do length over dx? It's because if you have a really small area, does the resistance go up or down? It should go up. Right? The smaller you make your area, the bigger the resistance is to heat flow. So to make that bigger, we just take L divided by dx. Okay, so that's our rate equation there. We can then, let's see. Yeah, so let's rewrite this as dQ dot is equal to TH minus TC. And then our total is just one over UA, right? So let's use that definition. This becomes UA times now dx over L. So just bring that to the numerator. Okay, so now we have a rate equation for our Q dot in this set of equations. And let's go then and rewrite our differential equations using this definition. Okay, so first let's do this for what, the hot equation. So this becomes, the hot equation becomes UA times TH minus TC times dx over L is equal to minus C dot H dTH dx dx. Okay, we can write the cold equation similarly. So it's UA times TH minus TC times dx over L is equal to minus C dot C dTC dx dx. Okay, and then we could actually solve these for our dt's, our derivative term. Do I want, yeah, let's do that just to have that handy. So that becomes what? dT H dx is equal to minus UA over L times C dot H times TH minus TC. Okay, and then the cold one is dTC dx is equal to minus UA over L C dot C times TH minus TC. Okay, so these now, I've done just a little bit of algebra, added in my rate equation, and I've solved for now this differential equation in terms of dTH and dTC. Again, these are coupled, but we also need to think about boundary conditions for each of these. I'm going to have two equations. I'm going to need two boundary conditions for this. Right? Two equations that are first order, I need to have two boundary conditions. So my boundary condition here on the hot side, well, it could be kind of anything. Usually we know the temperature coming in, right? And so the temperature coming in on the hot is going to be, let's look up here. So I have temperature, my hot is coming in at x equals 0, and my cold is coming in at x equals L. So I'm going to write the boundary conditions that way. So we'd say TH at x equals 0 is equal to some TH in, some temperature that we know coming in on the hot side, and same thing for the cold side, but at x equals L. So the boundary condition here, right, this is TC, x equals L is equal to TC in. Okay, so now the task is to figure out how to solve these coupled equations together. So we want to come up with a solution for these together. Because the TH and TC are not independent of each other. They're transferring heat together, so they have to be solved together. One way to do this, let's see, I didn't leave myself a whole lot of room here, but let's draw a line. So, okay, one way to do this is when you have coupled equations like this, or equations in general you want to solve together, we could actually subtract the two equations from each other, or subtract one from the other, and write it as a single equation. So that helps a little bit to see where to go with this. So I'm going to do that, and I'll just write the result here. So this becomes, subtracting the two equations, we get the following. We get d, so it's going to be d of t h minus tc over dx is equal to minus ua over L times t h minus tc times, squeeze in here, so times 1 over c dot h minus 1 over c dot c. Right, so you can see all I've done there is taken the two differential equations, subtracted the cold from the hot, and we end up with that equation. It's maybe not entirely clear how to solve this yet. Right? Well, what do we need to do to solve this? Well, we still have these two variables, th and tc. But like I said, they're not really independent of each other. At any given x location, there's a th and tc exchanging heat with each other. And so really what we could do is we could solve this equation in terms of a temperature difference at a specific position, because that's really what's driving the heat transfer. So I could introduce this substitution and say, okay, theta is equal to th minus tc. Right? So theta as a function of x is equal to th as a function of x minus tc as a function of x. This single variable theta then lets me solve this differential equation. So I can then rewrite this as d theta dx is equal to minus ua over L times theta times 1 over c dot c minus 1 over c dot h. Okay, so now you can see this is actually a pretty easy equation to solve. It's separable. We can bring the theta over to the left and x to the right. So let's do that. We end up with d theta over theta is equal to minus ua over L. Let's see, c dot c and c dot h are constants. So this becomes 1 over c dot c minus 1 over c dot h. Sorry, did I do that backwards? I'm sure I got this. Sorry, I flipped the order of these up here. So it should be c dot h minus c dot c. I'm subtracting cold from hot. C dot h minus c dot c. And then let's see what's over here. Times dx. Okay, hopefully we got that. So d theta over theta, ua over L, 1 over c dot h minus 1 over c dot c times dx. So we've separated it, now we can actually solve it. This just is an integral, right? We're going to integrate here, integrate here. For the integral, we could do either indefinite integrals and then enforce boundary conditions, or since we could do a definite integral where the boundary condition locations match, let's just do that instead. So we are going here from what? Theta at x equals 0 up to theta at x equals L. And on the right-hand side, we're going from x equals 0 to x equals L. If we do this, then we end up with ln of theta at x equals L over theta at x equals 0 on the left-hand side. And that's equal to minus ua, or minus ua times this 1 over c dot h minus 1 over c dot c. Okay. So I now have an equation, right? This is a solution to this equation. In terms of the condition at the left, x equals 0, and the condition at the right, x equals L, and everything on the right is a constant. So this is now telling me something about how theta behaves. I can go back and substitute in my temperatures and end up with the final solution, which is ln of, let's see, theta at x equals L is going to be TH out minus TC in. Think about that. So theta at x equals L, I could look back up here. Right, at x equals L, I have TH out, and I have TC in, so that's my temperature, or my theta evaluated at x equals L. At x equals 0, I have TH in and TC out. So we'll go back and write that here. So we have TH in minus TC out. And that's equal to minus UA 1 over C dot H minus 1 over C dot C. Okay. So now we have a third equation. This is our third equation that we need to solve the system of equations for, before we have everything in, for Q dot in terms of TH and TC. Now we have this third equation that we can use to relate the heat transfer or a counterflow type heat exchanger based on what the UA and the C dots in the, that are present in the flow. Any questions on this? This is this same analysis you would use. Yes, so you now from here, we can either go to formulations that are in terms of log mean temperature difference or formulations that are in terms of effectiveness NTU. So this is like the intermediate, this is the solution that you would use to develop those, which is what we'll do next. Yeah. So that question, the log mean temperature difference, that method is used to characterize kind of the average temperature difference for heat transfer between two flows. Other questions? Okay. So maybe put a star by this, right? This is only for counterflow. You are asked for parallel flow or cross flow, counterflow. You would not want to use this equation.